Welcome to lecture 11 for EE311. Today we are going to finalize single stage amplifiers and we will start with multi-stage amplifiers. For the bipolar transistor amplifiers, now we are going to define the small signal range. As you may remember, the main problem with amplifiers is that they are not linear. So when you have an amplifier, let's say, when you have an input at some frequency, let's say f1, maybe I can draw it in it. So when you have an amplifier, you have a sinusoid at frequency f1. If the gain is A, you want to have a signal at f1 where the amplitude is, let's say, A times V in. And you want to have this thing for a range of different frequencies. So when you have different frequencies f2, f3, f4, at the output, what you expect is the output should be the combination of all these inputs, let's say Vi times A. You want to have all of them to be multiplied by the same gain. So that's the definition of linearity. In nonlinear amplifiers, the gain changes depending on the signal amplitude or depending on the signal frequency. In another approach, I can show it like this maybe. Between input and output, assume that this is origin, V out, V in, we expect to have this gain slope constant. But in reality, this is not true. This is maybe valid for, some region. So this is ideal. This is practical case. And that's the case for transistors. So when you think about a bipolar transistor, remember that a transistor is a transconductance amplifier. Your input is this one, your output is the collector current. And when you draw IC versus VBE, you see something like this. I mean, maybe it's not exactly the same, but the critical thing is the linear region is limited. And in this linear region, guess what is the slope? What is the slope for this linear region? If you said GM, that is true, because in this linear region, I say that IC is equal to GM VB. And this linear region is named as small signal range. Now the question is this: how small should VBE so that I can have linear amplification? Because in the other regions, when I go above small signal range, this assumption is not true anymore. There will be some undesired terms in here, and because of that, you cannot have this linear amplification. So small signal range is this: how small should the input be so that my output current is still GMVBE? In other words, I can use small signal model only for this small signal range. So let's go back to previous slide and clear this page. And in fact, I know that IC is equal to is exponential VBE divided by VT. There's one important thing in here. Please take a look at the notation. This is both DC and AC. This is as well, both DC and AC. So this expression is valid for both AC and DC. This is a very general expression. In the previous slides, I used ICS instead of IS in here, but they are the same, so don't worry about them. And I wrote the same expression in here. So now I have both DC and AC, in here. So if you continue, you can write it in this form. And then you can make a simplification because I know that VB is small. I am dealing with small signal, right? So this VB is small. And in that case, I can write e to the power VB divided by VT as approximately as 1 plus VBE divided by VT. This is coming from e to the power x is approximately equal to 1 plus x for small x values. So by using this, I can write this thing as in this form. Okay. If you don't want to make this approximation, you can use Maclaurin series expansion. It will provide the same thing. So in that case, you need to write e to the power x as, if you don't want to use approximation, you can write it as 1 plus x squared divided by 2, x cubed divided by 3, or something like this. And you know, it will end up with the same result, so you don't need to worry about it. Okay. Therefore, or in fact, you know what we have to do? We have to make a correction in here. So I'm not going to use this simplification. I'm going to erase it. And I'm going to use this expansion. So forget about this thing. So I'm going to use this expansion. And in that case, this value will be equal to 1 plus VBE divided by VT plus VBE squared divided by 2VT VBE to the power n divided by n factorial. So this continues like that. But please keep in mind that VB is smaller than 1, so it's a small signal. So this is small, which means that VBE squared is even more smaller. This term will be much negligible. So if you use that, then IC will be equal to IS e to the power VB divided by VT times 1 plus VB divided by VT, so on and so forth. Look at the first term in here. This is 1. And this is IC, DC IC. So this thing is in fact equal to IC plus, this is DC, IC divided by VT VBE plus IC divided by 2VT VBE squared, and so on and so forth. So this is my DC expression. This is the DC. This is GMVBE, the first AC component, and it is quite reasonable because it's the linear component. So this is GM VBE. This is second harmonic. Assume that you are using a sinusoidal input. VB is a sinusoid, let's say. In that case, this term will be at the same frequency, but the second one is sine square, so you start seeing some undesired components. So this introduced the second harmonic. And the others are the other harmonics, but the good news is this term is definitely larger than this one, and this one will be definitely larger than the other one because VB is less than 1. So for linear assumption or small signal operation, I have to show that this term is significantly larger than the rest of them. So for that purpose, IC divided by VT, VBE should be much smaller than IC VBE square divided by 2VT. So let's work on this thing. What I am saying is IC divided by VT VBE should be much larger than IC 2VT VBE square. So what does this mean, this much larger? Let's say at least 10 times larger. So this may change from textbook to textbook. In general, 10 times larger is good enough. So people use this notation, and therefore they say that IC divided by VT VBE should be larger than 10 times IC divided by 2VT VBE square. These are going to cancel, and VBE should be and there should be a square in here. Sorry for that, I guess. Did I make a mistake? Yeah, this should be square as well. This should be a square in here. Therefore, I will have square in here, square in here. So this is gonna cancel out. VB should be less than VT divided by 5, which is 5 millivolt at 300 Kelvin or room temperature. So this means that for small signal operation, VBE should be less than 5 millivolts at room temperature. If you can satisfy this, then you can guarantee that your amplifier is in small signal range. Here is an example. Think about common emitter amplifier. Assume that I use a source with no internal impedance for the sake of simplicity. And let's assume that the question is input signal maximum value for small signal operation. I have to check VBE first, of course. This VB should be less than 5 millivolts. And in here, emitter is AC wise grounded. So VB is equal to, in fact, Vs in here. So from this, I can say that Vs, or the input signal amplitude, should be less than 5 millivolts. if I have common emitter with degeneration, let's do it very quickly. If I don't have that bypass capacitor, let's say, and I use the same source with no RS, let's say, Vs. Again, the same question, Vs max for small signal, let's say. Again, the same thing. I have to check this VB in here, and I know that VB should be less than 5 millivolts. Now I need to write Vs in terms of VB or vice versa. If you imagine the T model in here, you can see that I have small RE in here and R4 in here. Or you have R pi in here and reflected value of R4 in here, beta plus 1 R4. Both of them will result in the same thing. So thinking about the T model, R4, RE, VBE. Since I don't have any source resistance, this is Vs. So I can say that Vs is equal to R4 plus RE times VBE divided by RE. So Vs should be smaller than 5 millivolts times R4 plus RE divided by RE. And this term is larger than 1. And Vs can be something larger than 5 millivolts. So let's use some typical values, numerical values, let's say. Let's say RE is 25 ohms and R4 is given as 50 ohm, let's say. In that case, Vs is less than 15 millivolts for small signal operation. And this tells me that degeneration improves the small signal range. So maybe we can write it in here. Degeneration improves small signal range. And this is quite logical. Why? Because nonlinearity improves with gain. When you increase the gain of an amplifier, distortion increases, nonlinearity increases. When you decrease the gain, it becomes more linear. So that's what happens in here. Common emitter with degeneration. Degeneration decreases the gain, so the linearity should be improved. So your small signal range increases. When you take out this degeneration, gain increases, but then you sacrifice from the linearity or the small signal range. Okay, so please go over this derivation, and please note that I made a small mistake in here, which I corrected later on. IC divided by VT, IC divided by 2VT square should be in here. For the third term, IC divided by 6VT cube VBE cube should be in here. But you don't need to worry about these other terms. You just compare these two terms with each other and try to ensure that this thing is large enough compared to the second harmonic so that you can assume linearity. So to repeat once more, common emitter and common source amplifiers are good voltage amplifiers, and they form the gain stage of the multiple or multi-stage amplifiers. Common collector and common drain. They amplify current but not voltage, and they are good voltage buffers. Unity gain can be achieved, of course, with a good design. Good design means that, of course, you want to make 1 over Gm much less than the load resistance, or small RE much less than the load resistance. For common base and common gate, you have unity gain current buffers. And for these two, by using degeneration, you sacrifice from gain, but linearity, input resistance, output resistance, and stability improves. So degeneration sacrifices from the gain, but the other parameters are getting better and better. For this gain values, there are different notations. Please check your textbook for some of them. So please check Cedra and Smith for these definitions. Up to now, we always use this simple gain expression, V out divided by Vi. But there are different gain definitions, like open circuit voltage gain, which means that you make the load open circuit. In other words, you make RL infinite. So they name it as AV0 gain when RL goes to infinity. Similarly, the input resistance can be defined like that. Rin is Vi divided by Ii when RL goes to infinity. Current gain, short circuit current gain. So please be aware of these definitions and check them from Cedra and Smith so that you are familiar with it. So at this point, single transistor amplifiers are finished. Small signal range definition is known. You know about like DC biasing and DC analysis, and also small signal analysis. And from this small signal analysis, we can find 3 important features of an amplifier, which are Rin, Rout, and AV. Now we are going to combine this knowledge to have a multi-stage amplifier, and I'm going to solve a multi-stage amplifier example for further discussion.